Hi everyone, good day to all and thanks for attending my talk. My name is Yason and I am a security researcher from IBM X-Force, and today I'm going to share with you my research on the EdgeHTML rendering engine. The agenda for the talk: the first part, overview, is where I will give you a bird's eye view of the content of my presentation. The overview part is where I also discuss the diffing method I used to find out the major changes between EdgeHTML's and IE's MSHTML rendering engine. The second part, attack surface, is where I'll discuss the different attack vectors that comprises the attack surface of EdgeHTML. The third part, exploit mitigations, is where I'll discuss the different mitigations in place that attempts to make it difficult to exploit vulnerabilities in EdgeHTML and its dependencies. And finally, conclusion, is where I summarize the most important points and also discuss additional interesting research areas related to EdgeHTML. Some notes before we continue: a detailed white paper is available and it will be available on the Black Hat website. Among other things, it contains much more detailed explanation, a complete list of EdgeHTML classes and functions related to this presentation, and also a comprehensive list of references. Finally, all information is presented is based on Edge running on 64-bit Windows 10, build 10240, which was released around 3 weeks ago. The first version of the paper and presentation I sent to Black Hat was based on an older Windows 10 build, so you might have to wait a few more days for the updated presentation and paper to be uploaded in the Black Hat website. With that, let's begin. Overview. So first and foremost, what is a rendering engine? A rendering engine is the one responsible for parsing the markup, such as HTML in this case, retrieving and parsing any reference sources. In the example you see in the screen, a CSS file and an image file was retrieved and additionally parsed. And finally, the rendering engine will display the contents of the page in the proper layout with the correct styles applied, eventually resulting to the page you see on the screen. That's a simple high-level description of what a rendering engine is. However, looking under the hood, a lot of internal mechanisms are at work. For example, the EdgeHTML rendering engine here is hosted in the Edge content process here. Because the Edge content process hosts code that handles potentially malicious input, it is sandboxed using app container. Here. The content process is also running 64-bit by default. And also listed here are the additional exploit mitigations such as depth ASLR with high entropy and force ASLR enabled. Going back to EdgeHTML, it has several entry point classes here, responsible for handling certain types of input, such as markups, images, audio-video content, and more. These entry point classes may in turn call upon their dependencies to help with the actual parsing of the content. In addition to the mitigations applied to the Edge content process, where EdgeHTML is hosted, EdgeHTML and its dependencies have additional exploit mitigations applied to them. These are Stack Buffer Security Check, or GS, and the recently introduced Control Flow Guard. Finally, there are exploit mitigations specifically applied to EdgeHTML to handle certain types of memory corruption. These are the Virtual Table Guard and memgc. And that is just a quick rundown of the internal mechanisms at work. I'll discuss their details in the later slides. So earlier, I noted that I will also discuss the diffing method I used to identify major changes from MSHTML to EdgeHTML. This diffing method allowed me to spot potential changes in the attack surface, which I would eventually further confirm by looking at the code. It is actually pretty simple, and you just need either a Python script and a text diffing tool. It can be made a lot more complicated, but for the sake of discussion, the simplest way to do it is described here. If you think about it, because classes and namespaces suggest group of related code which may in turn correspond to a program feature or functionality, diffing them may give us an idea if a feature or functionality was removed or added. So using IDA-Python, I wrote a script to enumerate all functions and variable names, and then extract their namespace or class portion. I sorted the resulting namespace list, removed the duplicates, and dumped the namespace list into a file here. Then finally, I diff the resulting namespace list using the standard diff tool, and the result will be something similar to this. Here's what the output looked like in a text editor that supports the diff output format. In the first output, the following remove classes suggest possible changes in the support for EMF and WMF images. The second output, which lists new namespaces under the CFast DOM namespace, suggests new DOM object types that are exposed via the DOM API. Some interesting output you will find includes new namespaces or classes that suggest ported code from another rendering engine. The example shown suggests ported code from another rendering engine, Blink in this case, for the new web audio support in EdgeHTML. Of course, the method has its caveats. First, the results are suggestions. Further analysis is needed because it might be the case that a class or a namespace might have been renamed. If that is the case, you will find a new namespace plus a deleted namespace. Additionally, the method of course requires the availability of symbols. Finally, this simple diffing method can be used to diff functions and method names to identify the changes in functionality of classes, for example, or strings. The new strings may give you clues about what the new functionalities are. And finally, imports and exports. New imports suggest new libraries and functions being used by the binary, and exports suggest new functionalities exposed by the binary. So with that, let's move on to the discussion of EdgeHTML's attack surface. In the next slide, you see a diagram like the one you see on the screen. The left side describes the type of input, and the center names the EdgeHTML class that processes the input. And the rightmost side is the library used by the EdgeHTML class to perform the actual parsing of the input type if applicable. Note that the listed EdgeHTML class are the entry point class. Most of them use other HTML classes for the processing. The purpose of listing them is that you can use them as a starting point when you want to analyze how EdgeHTML handles certain types of input. For example, if you want to understand how XML-based markup parsing work, you can begin by setting a breakpoint to all methods of the CXML pre-class and then start your analysis from there. The first set of attack vectors are the markup and style parsing performed by EdgeHTML. If you look at the parser for HTML and XML-based markups, you'll notice that there are two sets of parsers. The first parser are the pre-parsers, here and here. They basically perform the initial parsing of the markup and pre-download required reference resources such as CSS files, image files, and then they also store the parse tags to get to a tag stream. The post parsers, here and here, fetch the tags from the tag stream, performs additional parsing if necessary, and then eventually resulting to the creation of DOM objects that represent the parse tags. EdgeHTML uses its own internal classes for parsing HTML and CSS files. For XML-based markups such as XHTML, SVG, XML, EdgeHTML uses XMLite for the XML parsing. There's also an XSLT filter that first checks if the XML file is referencing a style sheet. If it is, the XML file is first transformed and the resulting output is fed back to the parser, to the markup parser. This XSLT filter depends on XMLite for the initial scanning of the XML in order to identify if it is referencing an XSL style sheet. And then it uses MSHTML6 for the actual transformation of the XML. Finally, code for supporting binary behaviors, which includes binary behaviors such as VML, was removed in EdgeHTML. That in turn further contributes to the attack surface reduction in EdgeHTML. Mentioned in the markup parsing was XMLite. XMLite is a lightweight XML parser and advertised as a performant XML parser. Therefore, the reason it is used for the parsing of XML-based markups. EdgeHTML specifically uses the XMLite's iXML reader interface when reading the XML nodes from XML-based markups. So for XML-based inputs, one of the first code to touch the XML file will be in XMLite. I also mentioned that EdgeHTML also uses MSHTML6 for the XML transformation. EdgeHTML specifically uses the iXML DOM document interface for loading the XML and the XSL style sheet and then performing the XML transformation. What this means in terms of attack vector is that the attacker can remotely reach this XML loading and transformation code in MSHTML6 via an XML file that references an XSL style sheet. The second set of attack vectors I'll discuss are the image decoding code. The image decoding routines can be remotely reached via a direct link to the image or various HTML tags. The names of the HTML classes that handles image processing starts with the string C, img, task WYC. However, these HTML classes just relies on the Windows imaging component library for the actual decoding of the image. An interesting change is that in EdgeHTML, WMF and EMF image support by a GDI was removed, therefore reducing the attack surface in terms of image processing. As mentioned, Windows imaging component is used for the actual image decoding. Therefore, the image decoders in Windows imaging component are remotely reachable to an attacker via the rendering engine. Windows imaging component is a built-in Windows component that any application can use for image decoding or encoding. EdgeHTML uses this IWIC imaging factory crate decoder for instantiating the decoder for a particular image format. After image decoding, we now go to audio and video content decoding. Audio and video content can be passed to the rendering engine via a direct link or via the audio and video tags. The CMediaElement class in EdgeHTML uses the Media Foundation library for the actual decoding of the audio-video content. Also, in addition to media content processing, EdgeHTML supports audio-video captioning via the track tag. EdgeHTML supports two captioning standards, TTML and WebVTT. TTML is XML-based, therefore EdgeHTML uses XMLite for the parsing. WebVTT, on the other hand, is a simple line-based text format, and EdgeHTML has the internal parser to parse it. As mentioned, Media Foundation is the component used by EdgeHTML for decoding audio and video content. Similar to Windows imaging component, it is a built-in Windows component and it can be used by other applications for audio and video playback. It is a rather large framework supporting a number of media container formats and codecs. EdgeHTML specifically used the IMF Media Engine interface of Media Foundation for setting up the media source and controlling playback. Again, similar to Windows imaging component, Media Foundation is another security critical library because its decoder are reachable to an attacker via the rendering engine. Another attack vector, of course, is the font rendering in EdgeHTML. Using the font face CSS rule, arbitrary fonts can be passed to the rendering engine. EdgeHTML supports TTF, OTF, and WOF fonts formats, and they are rendered via direct write. If the font format is WOF, the compressed TTF or OTF font is first extracted and then passed to direct write. An interesting change is that EOT font support was removed in EdgeHTML. Because the parsing of EOT fonts requires the use of T2 embed and the GDI library, The number of libraries depended upon by EdgeHTML to render or parse fonts was reduced. Therefore, another attack surface reduction in EdgeHTML. As mentioned, direct write is used for the font rendering in EdgeHTML. Direct write is part of the DirectX family of APIs. Unlike GDI, direct write parses the font in the user mode process where it is hosted. Therefore, the font parsing code is sandboxed in the same Edge content process that hosts the rendering engine. Direct write is discussed in the excellent One Font Vulnerability Troll-Demo presentation. Needless to say, direct write is another security critical library because its font parsing code are remotely reachable via the rendering engine. Lastly, one of the largest attack surface in the rendering engine is the DOM API. Via the DOM API, JavaScript can interact directly with the DOM objects in the rendering engine. These DOM objects may in turn execute code in other internal rendering engine objects and may invoke code in the libraries they use, if applicable. Here is an example. JavaScript code calls document.write. In the rendering engine, code that transfer call to the DOM object is executed. The DOM object in turn will invoke methods in other internal rendering objects. Because of this, DOM API calls can change the state of the DOM tree, the DOM objects, and other internal rendering engine objects. And because of unexpected state changes, unexpected DOM API call input, or incorrect state when a DOM API is called, memory corruption vulnerabilities may result. An example is the use after free illustrated on the screen. In this particular case, MSHTML ed object was unexpectedly freed when document.write was called, resulting to a use after free condition. Using the diffing method I described in the overview part of this presentation, 80 new DOM object types were found. These new DOM object types represent new code or code paths that are reachable to an attacker via the DOM API. The complete list can be found in the white paper. And as an example, this listing shows the new DOM object types to support the new XPath API and the new XSLT API in EdgeHTML's DOM. Next, the properties and methods of DOM object types can be enumerated using JavaScript for-in statement. And another way to enumerate properties and methods is via query in IDA's names window. Once you have the list of properties and methods, you can also diff them to identify changes in already existing DOM object types. In the example, DOM document evaluate is a new method that is used for evaluating XPath expressions. Finally, though technically not part of the rendering engine and are performing another set of complex parsing and rendering themselves, the built-in PDF renderer in Windows and the pre-installed Adobe Flash Player can be considered as just one of the many dependencies that EdgeHTML uses to render their respective file formats, because they are pre-installed and they can be instantiated by default. From an attacker standpoint, being able to instantiate additional complex renderers have certain advantages, such as one, these complex renderers have another set of attack surface and vulnerabilities that attackers can leverage, and two, their functionalities can be repurposed to bypass exploit mitigation. An example is when FlashJIT generated code was leveraged to bypass control flow guard. And another example is when exploits use the well-known flash vector object corruption technique to bypass ASLR. Though this had been mitigated, they showed us how software functionalities can be leveraged for exploitation. The flash vector mitigation was described in Google's Project Zero blog. The FlashJIT CFG bypass mitigation will be described in a later slide. To summarize, in the area of image and font rendering, EdgeHTML attack surface had been reduced because of the removal of support for EMF images, WMF images, and EOT fonts. The code in the libraries that process these file formats had a history of remotely exploitable vulnerabilities. Removal of support for BML also further contributes to the attack surface reduction in EdgeHTML. However, as with many other modern browsers, new features are added. And these new features are exposed by new DOM object types, properties, methods, and updated markup and style specifications. In the case of EdgeHTMLs, new attack vectors were found in the DOM API in the form of new DOM object types and the addition of new properties and methods in already existing DOM object types. Also, the following libraries are identified as being used by EdgeHTML. XMLite for XML parsing, MSHTML for XML transformation, Windows Imaging Component for image decoding, Media Foundation for audio-video decoding, DirectWrite for font rendering, and the built-in WinRT PDF renderer for PDF rendering, and of course the pre-installed Adobe Flash Player for flash rendering. By identifying how these libraries are being used by HTML, we can further recognize their importance, since now we have an additional understanding on how they are being used by EdgeHTML and how attackers might be able to reach code in these libraries via malicious input. Now that we have an understanding of EdgeHTML's attack surface, let's now take a look at the exploit mitigations that an attacker will need to bypass in order to successfully exploit a vulnerability in EdgeHTML or any of its dependencies. In this part, I'll first discuss the exploit mitigations applied to the content process where EdgeHTML is hosted, because that would affect how EdgeHTML vulnerabilities are exploited. Next, I'll discuss the mitigations applied to EdgeHTML and the EdgeHTML dependencies I previously discussed in the presentation. And finally, I'll discuss the mitigations applied specifically to EdgeHTML. With each mitigation, I'll also discuss known published bypass or weakness that were discovered or researched by various security researchers. So let's begin. In 64-bit Windows 10, the Edge content process that hosts the EdgeHTML rendering engine is by default running 64-bit. 64 bits mitigates traditional heap spraying, which involves blindly spraying the heap with attacker-controlled values, and the attacker will be fairly successful in landing the controlled data at a particular address. The content process also has depth and ASLR operating with high entropy and forced ASLR enabled. High entropy ASLR gives additional entropy to where memory regions can be relocated, while forced ASLR prevents loading of DLLs that do not support ASLR from being loaded at a static address. Previously, attackers had found different ways to load non-ASL DLLs in browsers and use them to bypass ASLR in depth. With forced ASLR, those techniques are mitigated. App Container, on the other hand, is a process isolation mechanism first introduced in Windows 8 and was used in IE's Enhanced Protected Mode Sandbox. In addition to limiting read and write access, App Container also limits the process capabilities such as network capabilities. It is a much better sandboxing mechanism compared to low integrity, which only limits the process write access. This table is the comparison of the mitigation applied to the content process of Edge and IE on different Windows versions. You'll notice that the mitigations applied to the Edge content process is similar to that of Immersive IE in Windows 8, where they are both running 64-bit and sandboxed by App Container. In contrast, Desktop IE on Windows 10, Windows 8, and Windows 7 all runs 32-bit and only sandbox using low integrity by default. Now that we know that comprehensive exploit mitigations are applied to the content process, the next question is that, are there any published bypass against those mitigations? For 64-bit, depending on the vulnerability, a relative heap spray may be possible in cases where the vulnerability involves a valid heap pointer being added an attacker-controlled or erroneous value in a pointer computation. Since the bug already involves a valid heap pointer, the attacker would just need to groom the heap so that the attacker-controlled data will be relative to the heap pointer. For ASLR and consequently depth, since forced ASLR is enabled, which means loading of non-ASLR DLL is not possible in Edge, That leaves an attacker with two options to bypass depth and ASLR in Edge. The first one is to take advantage of pointers in predictable memory regions such as shared user data. And the second one is to use a vulnerability to disclose memory contents. Because Microsoft is actively removing pointers in shared user data, attackers are now mostly left in using a vulnerability to disclose memory contents. A common technique is to use a vulnerability to modify the length of an array in order to have a read-write-anywhere primitive. Finally, for app container, there are several ways to escape the app container sandbox and other sandboxes for that matter. This includes exploiting kernel vulnerabilities, since code can still interact with the kernel in multiple different ways, even when it is sandboxed. And the kernel mode vulnerabilities allow elevation to a very high privilege level. We can expect that a large share of sandbox escape will be via kernel mode vulnerabilities. Another option is exploiting broker processes. Sandboxing technologies uses a broker process in order to perform privileged actions on behalf of the sandbox process. These brokers may in turn have vulnerabilities that an attacker can leverage to escape the sandbox. Finally, there are some resources that sandbox process still has write access to. If these writable resources are trusted and used by a higher privileged process, you may be able to control the behavior of the higher privileged process and eventually use that control to escape the sandbox. So that's it for the content process mitigations. I'll now discuss the additional exploit mitigations applied to EdgeHTML and its dependencies. Most of you already know GS, and this mitigation is thoroughly discussed in various papers. But since this is an applied mitigation, it is included here. GS is applied to EdgeHTML and its dependencies. This mitigation involves storing a security cookie in the stack just after the local buffers, and then checking the security cookie before the function returns to make sure that the return address and for 64-bit compiled code, the saved x64 registers were not overwritten via buffer overflow. For the weakness, as you might have guessed from looking at the diagram, it will only detect a linear overflow. But if an attacker has the ability to specifically control where to write data to, such as a controllable stack buffer index or pointer, the attacker can write anywhere beyond the stack cookie and therefore will not be detected by the chat. So this mitigation is effective against linear overflow, but not if an attacker controls the stack buffer, pointer, or index. Next, a recently introduced exploit mitigation applied to EdgeHTML and its dependencies is control flow guard. When CFG is enabled, the compiler will add checks to ensure that the destination of indirect calls is valid. This exploit mitigation attempts to detect and prevent abnormal control flow, which can occur if an exploit is trying to redirect execution to rope guides in select executable code addresses in order to bypass depth. Internals of these exploit mitigations are well researched and published in various papers and presentations. One published bypass technique is by taking advantage of Flash JIT generated code, which due to its dynamic nature, any indirect calls made inside it will not be covered by CFG. This bypass technique, however, is now mitigated in Flash. The mitigation involves additionally JIT generating code that performs a CFG check, which is basically generating a call to this function whenever a call instruction is generated. Other published ideas to bypass CFG includes jumping to valid API address such as load library with a DLL and a UNC path. A requirement, of course, is that you will need to control the API call parameter. Another is overwriting stack data such as return address on the stack. The requirement, of course, is that you will need to find a way to disclose the stack address. We now go to the exploit mitigations specifically applied to EdgeHTML. An exploit mitigation applied to EdgeHTML but not in its dependencies is virtual table guard or VT guard. VTGuard was first introduced in IE 10, and its purpose is to detect an invalid virtual function table which can occur if an exploit had corrupted a C++ object in memory. This mitigation works by adding an ASLR randomized value, VTGuard, in the virtual function table of covered classes, which is then checked before performing a virtual function call. So if in this case, object O is modified, its virtual function table pointer will point to an attacker-controlled data. If the attacker don't have the value of VTGuard, the check detects the anomaly and will prevent further execution of the code. A shortcoming of this mitigation is that it is only applied to select EdgeHTML classes, and it can be bypassed if the address of VTGuard is leaked via memory content disclosure. Finally, another mitigation applied to EdgeHTML and its dependencies is memgc. In addition to EdgeHTML, the Trident rendering engine in IE on Windows 10 also have this mitigation in place. Similar to Memory Protector, which was introduced last year, this mitigates use after freeze by preventing the freeing of still reference memory chunks. However, unlike Memory Protector, which only checks the registers in the stack for references, memgc additionally scans the content of memgc chunks to pointer to other memgc chunks. This means that this mitigation covers more UIF cases compared to Memory Protector. The implementation of memgc is also much more sophisticated and in turn much more complex compared to Memory Protector. This is because it uses a separate managed heap called the memgc heap and for the allocation, and then it uses a concurrent mark and sweep garbage collector to reclaim unreferenced memgc chunks. For most of its functionality, it relies on the Chakra JavaScript engine memory management routines. The memgc heap and the garbage collector can be visualized as follows. Chunk of memory called segments are allocated using virtual alloc. Then these segments are divided into 40 96-byte pages. A continuous group of these pages are then treated as a block, which is in turn used in the allocation of similarly sized objects via a bucketing scheme. When an object needs to be allocated, memgc will allocate a chunk from the block in the appropriate bucket and then flag the chunk as root. Root means that the object or chunk is directly referenced by the program and therefore should not be garbage collected. So let's assume that the last allocation was in this chunk here. So we have here 4 root chunks in this block. So 1, 2, 3, 4. Then when an object is to be freed, memgc will attempt to locate the block where the object chunk is located. Let's again use this last chunk here as an example. memgc will zero out the chunk, so it will zero this out, and then clear the root flag of the chunk. By being unrooted, the chunk will be candidate for garbage collection if reference to it are not found. So in this case, we now have 3 root chunks, 1, 2, 3, and then 1 unrooted chunk, the last one. Garbage collection, on the other hand, is triggered when the total size of unrooted chunks reaches a dynamically computed threshold value. Once the threshold is reached, the garbage collection will be triggered. The garbage collector is uses a mark and sweep algorithm. Chunks that are not marked after the marking operation will be made available for reallocation. So the first thing the garbage collector will do is first reset the GC mark for all the chunks. So the GC marks for all these chunks will be cleared. Next, the garbage collector will mark all root chunks. So if we follow our example, these 3 root chunks here will be marked. And the last one will remain unmarked because it is unrooted. Next, the garbage collector starts scanning the contents of root chunks for references to other chunks. If a reference is found, the chunk is marked. So if, for example, the first chunk here has a pointer to this last chunk will be marked and thereby preventing it from being reclaimed by the garbage collector. Similarly, the garbage collector also scans the contents of the stack and the registers for references to memgc chunks and then mark them if references are found. So as a summary, if a pointer to an unrooted chunk is found in the memgc chunks or in the stack or in the registers, the unrooted chunk will not be reclaimed by the garbage collector, therefore mitigating a use after free condition. memgc is enabled by default. One way to configure it in both Edge and IE is via the override memory protection setting configuration, which can be set by the following register entry. If you are root causing a rendering engine bug, it would be best to temporarily set this to 0 and then enable page shift. As of this writing, memgc and memory protector still have no known bypass for covered cases, but as with other exploit mitigations, new bypass techniques may be developed in the future. However, note that exploits were demonstrated for UAF cases not covered by memory protector. Also, there are published research to using memory protector to bypass ASLR on 32-bit IE and approximating bottom-up allocation address range in 64-bit IE. So to summarize, comprehensive mitigations are applied to the Edge content process, EdgeHTML and its dependencies. With all these exploit mitigations in place, an attacker would need to invest more in finding exploitable vulnerabilities in EdgeHTML and another set of investment in developing reliable exploit for them. Nonetheless, motivated attackers will continually find novel ways to bypass these mitigations, and we could expect that these exploit mitigations will continue to evolve over time. To conclude, so it is inevitable that the attack surface of EdgeHTML and other browser rendering engines will continue to expand as new web standards are implemented. Most of the increase in the attack surface will come from the parsing and translation of new markup and style specifications, and most notably in the new functionalities that will be exposed to the developers and attackers alike via the DOM API. However, the increase in attack surface in EdgeHTML is balanced by the comprehensive exploit mitigations in place. Also, new or additional research in the following areas related to EdgeHTML will be both important and interesting, as they are libraries and features that are remotely reachable and are widely used. This includes internal research, code audit, and fuzzing of the following Windows component, which are used by EdgeHTMLs: XMLite, XML6, Windows Imaging Component, Media Foundation, Direct Write, and the WinRT PDF renderer. Some of them may already have public research such as Direct Write, and we need more of them so we have an understanding of the security posture of these security critical and remotely reachable components. Also, memgc is a new mitigation, and I only scratched a surface in terms of its internals. Further research of its internals, including the allocation and reclamation algorithms, how memgc heap can be groomed, and also checking if heap metadata attacks are possible. And of course, researching how memgc can be bypassed. These types of research will be beneficial to the understanding of its weaknesses and eventually improvements to memgc. Here are the references for the bypass techniques discussed in this presentation. A more complete list of references are available in the white paper. And thanks for listening, and if you have any questions, let me know.